So, I want to describe a little more detail of what happens when you have a reaction, electrochemical reaction. Okay. Let us say this is the electrode. Okay. You have water molecules here, dipoles. You have ions here, maybe chloride ion, H plus ion meaning it is surrounded by water molecules of course. Other ions with water dipoles, and they are lined up very near the electrode, they are lined up. Sometimes these can strongly adsorb and be present. So, that is one situation where we said I put the plus M and M bond in the brackets to say that sometimes we explicitly mention that, sometimes we just do not write that, we just write A minus solution becomes A adsorb, but it really means the metal is participating in that, that is on the metal it adsorbs. And there was a question that it is going to cause a resistance. So, it should work like a resistance. When you increase the voltage, current has to increase. See, the conduction within the electrolyte happens by ionic conduction. That means ions have to move here, it can be H plus, Cl minus, any one of those ions, all of them does not matter, they move. Electrons are transferred only from this metal to that area, and electrons can get transferred at this location, but in the solution an independent electron will not move. This solution is not an electronic conductor. If it is a liquid metal, electron can go through that, that is electronic conductor, but that is not an electrolyte. We are considering only ionic liquid here. Ionic liquids, it can be salt dissolved in water, acid or base in water. Mostly we are looking at aqueous or water based solutions. Okay. But even in other cases, in electrochemistry we normally look at ionic conductors in the liquid phase and electronic conductors in the solid phase. So, it does not look at situations where you have a film formed on the surface that offers a resistance, and then electron goes through that and it continues to go inside as an electronic conductor here. In that case, we can say this offers a resistance, it can increase the resistance of this system, that is okay. But we are looking at cases where an ion comes here and picks up an electron or gives an electron, that is a possibility, or there is a metal, the metal can lose an electron, can become ion, and then the ion crosses over the double layer and then goes into the solution. So, it is the ion that goes here, electron goes into this, or electron can come from here, M plus ion can come here, M plus ion can come and adsorb on the surface, and then the electron can neutralize it and form a metal. Okay. So, independent electron does not move from metal into the solution or from the solution into the metal. Independent electron is not really present in the solution. That is probably answering your question, but then a little late. Okay, we will take it up later then. So, we will continue with the derivation of the impedance expression for this. So, we have taken up a reaction which has electron transfer reaction and adsorption reaction, and we have written the mass balance equation, charge balance equation. We can get the steady state theta value, and we are supposed to derive this and get this. Okay. So, look at this, you can take this equation, expand it and truncate it after the first term. I am going to write this and we have done this before. So, I would assume that given enough time you can show that gamma d theta by dt when we apply a sinusoidal potential would give rise to j omega gamma d theta by de by dt term has given rise to this. So, this is the expression on the left side. On the right side we can expand, remove the terms which are EIC square and higher order, and then we can show that under DC conditions we are going to have K 2 DC Ca minus solution 1 minus theta SS is going to be equal to K minus 2 DC theta SS, because we would have set this to 0 under DC condition. So, that is how we have in fact derived theta SS. So, this expression holds true, and therefore, on the right hand side we would get terms like this B 2 K 2 DC Ca minus solution 1 minus theta SS minus B minus 2 K minus 2 DC theta SS minus K 2 DC C minus solution d theta by d E minus K minus 2 DC d theta by d E. So, instead of trusting that what I have written is correct, I would actually like you to try this and get this. So, what you should do is, first step is to write K 2 as approximately equal to K 2 DC 1 plus B 2 EAC. Theta SS is approximately equal to, I am sorry, not theta SS, theta is approximately equal to theta SS plus d theta by d E multiplied by EAC. K minus 2 is roughly equal to K minus 2 DC B minus 2 EAC. So, what we need to do is to substitute for K 2 theta and K minus 2 in that equation. This equation, right hand side, left hand side we have written it, right hand side we should substitute this and then multiply the terms there, then recognize that K 2 DC Ca solution 1 minus theta SS is equal to K minus 2 DC theta SS. That means, some terms will go away, some terms we are going to throw away saying EIC square is not significant, and then the remaining terms are going to give you this, that is my claim. Once the remaining terms are written down correctly, you can rearrange it, it is a matter of just arranging them, no algebraic manipulation.
So, what is the exact use of theta SS? Why we are calculating theta SS?
See, basically if I give you kinetic parameters, I would like you to be able to predict the impedance spectrum at a given DC potential. Okay. So, now the current depends on rate constant, it also depends on fractional surface coverage, which is theta. Okay. Now, on top of a DC potential we are applying an AC potential. Because of that, the rate constant will modulate, will increase and decrease. They will have certain value, on top of that value they will show a slight increase and decrease, because we are applying a small amplitude. Similarly, the surface coverage is also not going to remain the same. See, what happens is, in this reaction, it does not show up very well here. So, I will write it here, A minus solution plus metal gives us K 2 K minus 2. Okay. When potential changes, K 2 will change, K minus 2 also changes. Now, K 2 is, in this case, K 2 is going to increase when the potential increases, K minus 2 decreases. So, the change is not the same, it is in fact in the opposite direction. So, what would happen to emerge out? It is not going to remain constant when I apply an AC, it is going to show an oscillation, it is going to increase and decrease. the fractional surface coverage. Let us make up a number and say if I apply certain DC potential 0.2 voltage with respect to equilibrium, then I have 30% surface coverage. Now, when I apply an AC, it is going to oscillate maybe between 31 to 29 percentage. Okay. So, I need to know this value. So, I can tell the current is going to change from so many milliamps per square centimeter. It is going to oscillate around the DC, but this is how it is going to oscillate. This is going to be the amplitude, and we also see the theta SS will not be in phase with the potential. That means, when I start here, so if you look from this side, let us say this is 0, potential goes up, comes down and goes like this, fractional surface coverage under steady periodic condition. That means, initially there is going to be some transient, and after that it is going to oscillate with the same period, and it is going to be periodic, meaning whatever point I find here, after one period I will find the same point here. Initially it is not going to be like that, there will be short time when there is a transient. Now, the theta will oscillate with respect to time, current will also oscillate with respect to time. However, let me see if I can move to the other one. Yeah, this is nice. However, let us say we have given the AC potential some time ago, and by this time we are going to say this is when we start measuring t equal to 0. By this time it has come to steady periodic value for the current and theta everything. So, the potential goes like this, the current will not necessarily go with the same phase. If it goes with the same phase, this is how it will look like. Current may also show a phase difference. Theta will usually show a phase difference, unless the parameter values are aligned such that whenever one rate constant increases, the other rate constants also move in such a way that the fractional surface coverage does not change. So, what happens in those cases is theta is also going to have a phase difference. If there is no phase difference, all of them at time t equal to 0, they will start at this location. If there is no phase difference, it is going to go like this. If there is a 90 degree phase difference, it is going to go like this, or it is going to be plus 90 minus 90, depending on that it is going to show a shift. And this theta value where it is a starting or where its average theta value is not 0, it is some value. We are writing in terms of theta SS because at the DC we can measure the, or not we can measure, we can calculate the K1 DC, K2 DC, K minus 2 DC. We can calculate theta SS, we can calculate the current at that DC, and this AC current depends on theta SS. The AC current depends on the K1 DC, K2 DC and the exponents B1, B2 etc. And of course, it also depends on omega. So, what else can we write it on? Theta SS is an intermediate variable for us. It has some physical meaning. Theta SS is written in terms of K1, K2, K1, K2 DC, K2 DC, K minus 2 DC here, and in terms of CA minus solution.
Theta SS here is dependent on K2 and K minus 2 only, right?
K2, K minus 2 and CA minus solution. Yes. This is in this particular example. Another example, another mechanism, it is going to depend on certain variables, depends on what the mechanism is. Because we can assign a physical meaning to theta here, we would like to represent in terms of theta. Otherwise, I can write everything in terms of K1, K2, K minus 2, CA minus solution, CP minus solution, just what is convenient to us. But are you able to expand it and get it? Some of you? Yes? Okay. So, the calculations are done, we would get d theta by dE, and I can simplify some of the terms. I recognize K2 DC, CA minus solution, 1 minus theta SS is the same as K minus 2 DC theta SS. Therefore, on this side I can take this term and make it substituted with this term. So, it simplifies a little bit, otherwise it does not matter. If you are going to use a program to calculate this, you can use this way, you can use the original expression, you would get the same number anyway. When you write it, you want it to look with fewer terms, it looks better, we can write like this. So, d theta by d is necessary because when we expand IF in Taylor series and then truncate it, we would get certain terms. When we expand IF and approximately write this, we can write this in terms of all the parameters there. This is IF AC, we have done the expansion for IF yesterday. We have written it as IF DC plus IF AC, where IF AC is the term that comes in terms of EAC. EAC square and other terms are neglected. Anything that does not depend on EAC, which is just a constant, that happens to be the DC component. So, within that bracket you see a expression for d theta by dE, and in order to calculate it we had to use the mass balance equation and get that expression. Again, this just needs us to expand k values k1, k2, k minus 2 in Taylor series and truncate it after the first EAC. It requires us to expand theta in terms of theta SS plus d theta by dE EAC, truncate it at that level, take the product, rearrange, simplify, you would get everything, but you would get d theta by dE, we need to substitute for d theta by dE. Once you do that, you get IF in terms of EAC, take the ratio of IF AC to EAC, and what you get is the Faradaic admittance. Take the inverse to get the Faradaic impedance. Point here is it depends on omega. That means when I vary frequency, I will get a change with respect to the frequency. I will get a change in the current for the same potential change, I will get a change in the current. That basically means the impedance cannot be represented by a simple resistance. It needs, in this particular case, it needs a Maxwell element with a capacitor. Now, I think we also saw that theta SS will show an S shaped curve, very low potential it going to go to 0, very high potential it is going to go to 1. The current values here, I mean the DC current value I DC as a function of EDC. We do not need the Faradaic impedance expression for that, all that we need was this at DC. So, at DC you can calculate the K1, K2, K minus 2, you do not need the gamma value, you need K1 0, B1, K2 0, B2, K minus 2 0, B minus 2, AA capacitance is not necessary. This is supposed to be, I think, C minus solution, CP solution. Concentration, this is one example. You can take up other kinetic parameter values and see if system is little different or the concentration is different, what you would see. This case the DC current goes up and comes down. Physically what it means is that as DC potential is very low, reaction happens at a very low rate. Okay. P does not become Q unless the DC potential is significant. This is driven only when the potential is positive, this reaction will happen to a large extent. When the potential is 0 or negative, K1 becomes, if E is 0, it is just K1 0. If E is negative, it is going to decrease. When E is positive, it is going to be increasing. So, K1 becomes very small number, therefore, first reaction will not happen to a significant level when you go to low potentials. When you go to low potentials, K2 also becomes small number. When the potential is small, theta becomes close to 0. Now, this reverse rate is going to be K minus 2 DC multiplied by theta. K minus 2 will increase whenever the potential goes down, but theta becomes 0, therefore, the reverse reaction rate is also very low. So, what happens is when you go to very low potentials, the rate is low, rate of each reaction is low, and each reaction is an electrochemical reaction, but since each reaction is not significant, it is not happening to a significant extent, we get net current as close to 0. When the potential is very high, the surface is fully covered with the adsorbed species, that means the first reaction cannot happen to a significant extent, even though the rate constant is high, there is no bare surface exposed. Because there is no bare surface, the second reaction, forward reaction also cannot happen, it requires a bare surface. Reverse reaction in the second reaction, the rate constant is low, although the concentration of A adsorbed is high. So, put together this tells us that the current is going to be very low when you go to very high potential. The reason the current is more or less 0 is different. At low potential it is 0, at large potential it is 0, but for different reasons. In one case the surface is bare, another case surface is fully covered with this adsorbed species, but in both cases current is going to be very close to 0. In between, when surface is partially covered with the adsorbed species and the rate constant values are not close to 0, it is moderate, then you would get a positive current, it goes through this and decreases and comes down. So, if you take polarization curve, current versus potential, let us say it shows something like this, it may show something like this, it may show something like this, does not matter. If you take an impedance spectrum in the region where it shows a negative slope, when it shows a negative slope, it means around this region when I increase the potential, current will decrease. When that happens, the impedance spectrum at low frequencies will show a negative value. It usually starts like this, after that it may do this, it may do this, it may go like this, it would settle on the real axis. We have got data where it goes like this. We have seen data with a variety of, but if you go to low enough frequency, it will always settle at the negative axis as long as the slope is negative. Why do we need to go to low frequency? This is taken at DC. If you go to high frequency, the capacitive current will contribute to that, and this expression comes to negative value only when omega is close to 0. This is taken at DC, meaning I take potential here, I get the current value, I go to this potential, take the current value. If I go to that potential and slightly move, that is equal to going at a 0 frequency or low frequency. If I move rapidly, this potential dynamic polarization curve does not tell me what will happen. That is why we need impedance spectrum at this potential. This curve tells us what would happen if you are more or less at 0 frequency. Impedance spectrum low frequency data tells us d E by d I value when omega is tending towards 0 or low enough value. So, the relationship between current potential diagram and impedance curve is, this is current potential diagram, impedance curve, that is current potential diagram gives you I DC versus E DC, impedance spectrum gives you dE by di, which is going to be the inverse of the slope of this. Impedance spectrum at omega tending to 0 is going to be equal to the slope of the potential dynamic polarization curve.
Sir,
Yeah.
In YF equation, except omega, nothing else is dependent on EAC. In YF admittance.
YF does not depend on EAC, omega also does not depend on EAC. Omega is what we apply, the frequency.
Apply, right?
Yeah.
So,
YF is the ratio of IF to EAC. Yeah.
I'm just asking, in plots we won't get any versus EAC, right? Only we will plot with respect to DC.
You meaning in the impedance spectrum or you mean in the polarization?
Current versus potential, we have drawn a plot, right?
Current versus potential, the experiment is conducted like this. Ideally, you would go to potential, wait there, monitor the current. When it stabilizes, note the current. Go to next potential, wait for some time, monitor the current, when it stabilizes, record that current, and then we generate the curve. Practically what happens is, we start at a potential, scan it at a slow enough rate and monitor the current. The assumption is it is going very slowly, we consider that to be more or less at a steady state condition. It is like taking a picture, move there, stand, take a picture, move there, stand, take a picture. Okay. That is the theory. What we do is walk slowly and keep clicking, and we think it is going to be more or less similar. Whereas, an experiment like cyclic voltammetry usually will be like riding in a motorcycle or going in a car and taking picture. That is probably not going to represent the stationary position, but practically this is what you would end up doing most of the time. If you really want, you can do this case of going there and waiting and getting the current value and recording that. So, that is how the DC value is obtained. Impedance spectrum is you go to some DC potential, it can be at equilibrium, it can be some other potential, wait for some time, it will stabilize, then apply an AC on top of the DC. Again you have to wait for a short time to stabilize, typically short time, depends on the system, and then take data. The software will allow you to wait for certain time or certain number of loops and then take that. Usually commercial software allow you to do that. So, impedance spectrum is information just at this point or around that point at many frequencies, around this point at many frequencies, around this point at many frequencies. So, if you take impedance spectrum at multiple potential, you would get lot more information than taking only the DC current at that DC potential. On the other hand, if I take impedance spectrum only at this frequency, I mean only at that DC potential, I am not going to get information on how this is going to behave at other DC potentials. So, you should take polarization curve. Ideally, you should have impedance at spectrum at every DC potential, but that is not going to be happening at a few DC potentials spanning this range of interest. If your range interest is limited to this only, you probably want to take 3 or 4, 3, 4, 5 whatever number, depends on, again there is not much point in taking impedance spectrum around this, because if the 5 or 10 millivolt amplitude overlaps with the next point, you are probably not really getting lot more information. If this range is 300 millivolts, I can take every 50 millivolts I will take an impedance spectrum. If this range is 20 millivolts, I probably will not bother taking like 5 spectrum at 5 different DC potentials. But this is more of a practical aspect, but does that answer your question?
Yeah, that is what I asked. If for a given DC potential, if you change omega, IAC also will change, right?
IAC will change, yes, that is how we get the impedance spectrum. Otherwise, if it does not change, we will see representative of a resistance, at least they have a double layer capacitance. So, you will have a change in current, you will have a change in impedance. Yes, shall we proceed? So, I can write the expression for this, and for a set of kinetic parameters which I have given in the earlier slide, you can show that this is how the patterns will come in the complex plane representation, right, imaginary minus imaginary of impedance and the plus real value of this impedance. So, it basically the points are more and more dense here, which means it is settling there. As you go further down in frequency, it will just stay here. Of course, this is noise free data, it is synthetic data, right. When you measure, there will be some noise, but usually if the system is good, you would see it settling there. Sometimes you would see data where it goes like this, comes here, comes like this. Here, if you look at the IDC versus EDC, wherever this is taken, that would be a positive number, that slope is a positive number. That means, finally, it should settle on the right side. So, by looking at the current potential diagram, if the current potential diagram looks like this and you take impedance spectrum at this location, even before taking the impedance spectrum, you can tell I expect the impedance spectrum to settle somehow, maybe like this, maybe like this. Somewhere it has to settle on the negative axis, and if the experiment is done correctly, I know the slope value, it should settle around that point. It should settle at that point exactly, but experimentally there is going to be some noise. So, around this point I know the slope. So, d I by d E is known to me. So, I can calculate d E by d I, and that is where this number is going to be. Look at this curve, you can't tell that the impedance will have negative values at the real value. So, this type of impedance is called hidden meaning looking at the polarization curve you cannot tell that this impedance will go through the left plane in the complex plane. Those are not very common though. If time permits, I will create an example and show you one. Right now, I just want you to be aware of it, that if the polarization curve shows a negative slope, you should expect the low frequency values to settle at the negative real axis. If the polarization curve shows a positive slope, you should expect it to settle at the positive real axis, and the inverse of the slope should match with the point at which it settles with an experimental error. So, it is possible to do some consistency checks. It is necessary to do consistency checks. If you get impedance spectrum, we should do KKT validation. That is for that spectrum alone. When we get multiple impedance spectra at various DC potentials and you have DC current and DC potential, you should get that anyway when you do experiments. Taken at slow scan rate, then you should check whether the polarization resistance that you get here is matching with the inverse of the slope that you get. So, you have confidence in the data when the internal consistency checks show that there is a good match. Now, I can model those data using this circuit, okay, except that I have to allow negative values for the R2 here. This particular value is shown for the first spectrum which goes like this, all the elements are positive. For the second spectrum which goes like this, one of the elements is negative. You also see that there is a large capacitance value. It is just to show you that when you model the spectrum with the EEC, you will get values. R2 is negative, C3 is very large value. It is not easy to get 33 millifarad in a real capacitor. You can get it, it is not that you can't get it, but in the electrochemical system, we do not have to imagine that there is a negative resistance, we do not have to imagine that there is going to be a capacitor or an inductor. Without resorting to any of those, just by saying this is the reaction and this is the adsorbed species, when I modulate the voltage, when I modulate the potential, this happens to modulate like this. What happens is when I increase the potential, surface coverage becomes more, when I decrease the potential, surface coverage of this adsorbed species becomes less, when I do it at a very slow scan rate, very slow frequency. When the surface coverage becomes more, the net current actually becomes less in this range. So, when I go to from here to here up to some level, when I increase potential, surface coverage becomes more, current also becomes more. So, it is in the positive region. From here to here, when I increase the potential, surface coverage becomes more, and because surface coverage becomes more, this reaction slows down, this reaction, the vacant site becomes less, current becomes less. Because of that, when I increase the potential, current decreases. So, it appears as a negative resistance because I am taking dE by di, I am not looking at E by I. E by I is still positive here, this is the E value, this is the I value, that is still positive, but the slope which is dE by di is negative here. So, I get negative impedance, I can explain by physical processes rather than thinking there is some negative resistance, there is some inductance, it means adsorbed species. If you have capacitance, you can explain it with the adsorbed species. If you have inductance, same adsorbed species with a different kinetic parameter value can give it, or even the same kinetic parameter value at a different DC potential value can give you inductance. So, same reaction conducted at one DC potential, if you take impedance at that potential, can give you a capacitance. Another DC potential, the same reaction, same kinetic parameter can give you inductance. So, lot of times you will see people resorting to some phrases because they do not do this kind of analysis, they just look at the circuits they realize they have to model with an inductance, they go to the prior literature and then say this inductance may arise because of something, adsorbed species interaction. If you ask what is that adsorbed species interaction, it is very vague, whereas it is possible to explain using proper reaction with proper kinetic parameters, proper dependence of the parameters to the potential. When you change the potential, it has to change exponentially, that is what you would expect for a normal electrochemical reaction. The rate constant still changes exponentially, it is just the rate does not change like that, because rate involves k as well as theta in this example. So, I am not going to derive the expressions for this, but you can come up with your own variants of this reaction. I can say metal goes into metal plus adsorbed, that means there is a metal, it loses an electron and this surface area, this is from the side, this is metal, this is electrolyte. I can look at it as the front face of the metal and I can say this area metal has lost electron, therefore, it is adsorbed species, considered as an adsorbed species, it is not coming from solution. Okay. This can pick up an electron and become a metal again, metal atom again, that is the reverse reaction. It can also go into the solution, then it will leave a vacant metal again below that. If it goes into the solution, this becomes a normal metal again. At the same time, another metal can become metal adsorbed, and these depend on the first K1 and K minus 1 depend on potential, K2 does not depend on potential, because there is no electron transfer involved. For this, you should be able to write the mass balance equation, charge balance equation, expand the terms in Taylor series, truncate it, rearrange and get an expression for impedance. You should be able to write the DC potential versus current, take some values for the kinetic parameters and simulate or show this is how the current potential will look like, this is how the impedance at a given DC will look like. You can make the reverse reaction possible for the second step, that is again not going to depend on the potential. This is actually superset of the first example. This is the superset of the example we have seen before. Originally we said M going to M plus adsorbed, this is just a forward reaction, there is no reverse reaction, and M absorbed going into M plus solution again. So, I am creating little more complicated or a superset for this, superset for this. You can write this, but then this means the solution already contains sufficient amount of metal plus solution, that is a possibility. Okay. It is well mixed, but it already contains certain amount of M plus solution and that quantity is not changing when we allow it to dissolve or deposit. In all these cases, we assume mass transfer is fast, we assume solution resistance is negligible. If you have to take that into consideration, few more complications would come, that we will see later. I also want to show another example. I want you to think about this example. We go back to the original, metal going to metal plus adsorbed releases an electron, the metal plus adsorbed on the surface goes into the solution. We have seen this before. In addition, I can say this metal can become metal adsorbed, it is one step, next step it goes into solution, that is what you have seen before. I can say third, metal can directly go into solution and take or give an electron here, that means it is a parallel reaction, metal becoming metal plus adsorbed becoming metal plus solution. Of course, this happens with an electron transfer. In parallel, metal can directly go and that happens at a different rate, K3. Okay. So, if metal becomes metal adsorbed and the surface is mostly covered with metal adsorbed, then only this reaction will happen to a large extent, the third reaction will not happen to a large extent because there is no bare metal. Do you understand? This when it happens, it will regenerate the metal. A metal is there, it goes out, another metal below that is exposed. Whereas, electron is taken out, it does not go out. Until this goes out, the metal atom below that cannot lose another electron, that is the assumption here. So, this would give rise to another type of polarization curve.
But we can assume that some part of the surface is going directly into the solution, some part is releasing the electrons and going back.
Yes, that is the mechanism 3 here.
But you said that if the surface is releasing an electron and then going in the solution, then the back from that one will.
See, let us say this is metal adsorbed. metal has become metal adsorbed, taken an electron. Before this goes into solution, this metal atom will not lose an electron. It's already positive here. The neighboring atom below that will not be allowed to lose an electron, because it's already, this atom has lost an electron. Of course, you can ask the question, what about these? Can they lose an electron? By Langmuir isotherm model, we say whether this is M-adsorbed or neutral metal, it does not affect the rate of the other one. That's
I am saying that you said that in the K3 will be negligible in the case of third case, in case third.
no, if the rate constants are such that at some potential mostly metal is covered with metal adsorbed. Let us say this is fast, this is slow, that means it is not happening at a fast enough rate. This is also slow compared to the K1. Then at low potential most of the surface is bare metal. So, this will occur to some level, this will also occur to some level. When you go to high enough potential, most of the surface will be covered with M-adsorbed. That means, in this surface only possibility is K2, the second step can push it. This will occur, but to a small extent, because the vacant metal site is not that much, there are only few sites.
So, means we are assuming complete coverage.
It will happen only for certain values of K10, B1, K20, B2, K30, B3. I would like you to just visualize that possibility. I am not saying for this mechanism all the time it is going to happen like that. This mechanism, when K30 and B3 are very, very small compared to K1 and K2, then this mechanism is same as, pretty much the same as the mechanism with only first and second step. That is a variant, but generally unless I know the values, I can't tell this is going to happen like this, that is going to happen like that, etc. So, I have to take, normally if I get a spectrum, I will see if I can explain this based on whatever prior information I have about the system. If it is copper, I would say copper is going to copper 2 plus, but copper 1 plus is also stable, we can have salts of or oxides of copper 1. So, I would say copper will become copper 1, copper 1 will become copper 2, that is a possibility. Copper can directly become copper 2, that is also a possibility. If that is able to explain, and I do not see evidence for presence of copper 1 by any other technique, then that is good enough. If I do some analysis like XPS, it shows that there is a copper 1 present there, copper 2 is also present, then probably it is sensible for me to propose a model where copper becomes copper 1 becomes copper 2. If that explains it, well and good. So, I can propose a mechanism like this, copper becoming copper plus electron. Okay. This is adsorbed, copper plus becoming copper 2 plus, I can say it goes into solution. If this explains, done, but if I see it on the surface, I should say maybe this is what I should do. If this explains polarization curve as well as the impedance spectra, well and good, does not explain, what can I say? I will say okay, this is 1, this I will say copper plus, this I will say copper 2 plus, this is vacant. I am looking at from the side, this is electrode and this is solution electrolyte. So, I am saying this copper plus has to become copper 2 plus and then go into the solution, that is what our model says. You can say in addition to that, maybe I will say directly go into solution by giving one more electron. So, I can say copper plus adsorbed becoming copper 2 plus solution plus electron is also possible, that is going via this path or going directly. I can add one parallel path, this may be reversible, this may be reversible, this depending on what I know about the solution. Does the solution already have copper 2 plus? Am I removing it as quickly as possible, in which case reverse reaction will not happen if the solution does not have copper 2 plus. Knowing the situation, I can say it is reversible or I can say it is not possible, I have to take only the forward reaction into consideration. I can also say, why should I go through all this? I can say copper directly becomes copper 2 plus solution, copper directly becomes copper 2 plus adsorbed. These are all possibilities. You want to come up with a reaction mechanism that can explain the observed results, polarization results, typically impedance results, any other analysis that you do, maybe XPS, because normally you do not know the charge on the surface unless you do XPS. But whatever other knowledge you have about the system, the mechanism that you propose should account for those and explain the electrochemical results. So, reason I am showing few mechanism is so that you can come up with some mechanism, propose a mechanism, and you should know how to derive the impedance, you should know how to derive the polarization curves or the IF values, and then match with this. Optimization is the next step, but first given a mechanism, given a set of parameter, can you write the current, can you write the impedance expression. Next, you should come up with a mechanism for your system, and then for a trial value you should be able to write this, and then optimization has to be done as the next level of match. Yeah, one way.
Any change in polarization curves for these three reactions? How polarization curves looks like? Any difference?
You have to generate it and see. It is not that difficult. I am hoping by this and the next few classes you should be confident enough, you should be able to tell me any mechanism, as long as you guarantee me that the solution resistance is negligible and mass transfer is fast, rapid. I can tell you the current, I can tell you that impedance expression for any given DC, any given parameter. That is what you should be able to do at the end of this few classes. Now, you should be equipped with that, at least that is my goal. Now, what mechanism should you propose? Okay. We can get some hints under these conditions. If you get 3 loops like this, high frequency loop would come from double layer capacitance and actually not this, it is charge transfer resistance, this is polarization resistance, but that is all right. From one resistance here in parallel with the double layer capacitance, this we assume it is negligible for now. If I see 2 more loops, I cannot model it with this alone for a circuit. I should add one more at least. In the mechanism, you need at least 2 intermediate species, 2 adsorbed intermediate species to generate 2 curves here. These correspond to 2 time constants. Time constant is RC here. Out there it is going to depend on the K1, K2 etc., but if I see n number of loops, I can assign one loop to double layer capacitance in parallel with the resistance. The remaining number of loops would correspond to the number of adsorbed species in a reaction, as long as the reaction is fairly simple, including these reactions. In some exceptional cases, it is possible that the reactions are redundant, meaning you may have 10 adsorbed species, but effectively it may be able to give you only fewer number of loops. But I do not think we are worried about that. If you can manage 2 adsorbed species for now, at the end of this course I think it is good enough. With the same 1 adsorbed species, you can see there are many possibilities of reactions you can make. So, this gives you a hint on how many adsorbed species are necessary. It does not tell you what exactly is the mechanism. Okay. So, in a mechanism, in a system, let us just make up this thing. I have 4 DC potentials. At this case I have taken 4 spectra. One, 2, 3 and the 4th one is here. I will just first shows a loop like this, second shows a 1, 2, 3, 4. One reaction mechanism, it is possible that one reaction mechanism can be used to generate this or model this. Whereas, if I use a circuit for one, I have to use this circuit, second I have to use this circuit, third I have to use this with negative values, fourth I have to use this with negative value for another element. All that we see is this is one time constant, this is one time constant, this is one time constant. This can be modeled with one Hertzhard species. One Hertzhard species, but a simple reaction like this may not give you a curve which is going down. Therefore, I can't use this mechanism. If you take many reactions and generate the curves, polarization curve as well as the impedance for a variety of parameters, you can get a feel for what mechanism can generate this data. But you should know something about the system to say this intermediates are possible. You can't just randomly make up a mechanism. Without substantial evidence, it is not that good to do that. Okay. We will stop here today. I want to take up a very simplest reaction possible with two intermediates. So, it needs 3 steps. Okay. This I want to see another mechanism which is called catalytic mechanism, which is little different, little tricky. Once you know how to handle one Hertzhard, two Hertzhard, catalytic mechanism and EAR, which we saw just now, you should be able to write impedance expression and current for any mechanism with any number of species.